to organize this school, now as one of the organizers said, there is no way she's not gonna come to this school. And that's why I sent you an email as soon as we had the approval from ICTP-SAIFR. So thank you so much for being here.
Wonderful to hear. Thanks, Reinaldo. Okay, so let's see. I hope the sound is okay. Okay, I never have a feeling. Okay, so right. So I do not know how much background you have. It's always a tricky thing to prepare lectures, not to be too basic or not to be too hard. So I probably went for too easy, but maybe not. I don't know. Anyway, the first lecture should be very easygoing. It's about how do we know that there is dark matter, okay? So this is, wait, let me see. Like this, okay. More or less the, you know, how I will divide the topics in the lectures. So today, the first lecture will be these 2 points. So just a prehistory of like how we got to know in the 20th century what we know about the cosmology, but very basic level. And then the list of evidence for dark matter. And then after lunch, I will do more about dark matter candidates, signals and targets. And then tomorrow, go more into depth with gamma rays and how we actually search for dark matter, okay? Okay, so really I couldn't resist, I guess, with age. Like when you get older, you start to love history and how things really came together. So I couldn't really resist not to give you a very historical detour. And so, right, so I'm basically starting at the beginning of 20th century. So this is like really hundreds of years ago. But I thought it was nice how we actually come to realize how our universe is made. Okay, so at the beginning of 20th century, basically, what happened? It happened that before that, people had telescopes, they studied stars, and that was astronomy as we know it. Then at some point, they developed so-called astrophotography, basically. Photography was invented, you know, normal photography, and people and astronomers started pairing photographic plates with telescopes, which allowed them to have much longer exposures. So suddenly what we could see with the eye, we could see much, much more in depth. So this is the revolution that exposure on its own brings. And they realized that there are such things as nebulae on the sky. So before there were only stars, then they realized there are extended objects, and they were wondering, what are those? Okay. At that time also, and now as they had photographic plates, they suddenly started having big data. No, before they had few stars, then suddenly they had enormous amount of stars. More or less like we have now, always more and more data, and we now have ChatGPT and things like that. At that time, they basically were hiring women, like so-called computers, that would just look at those plates and try to classify the stars. It was a cheap labor. Okay, and among them, one of the biggest discoveries was that of Cepheid stars, because Henrietta von Leavitt was one, you know, in her group that realized that there are such stars that as you go in time, they're variable, and that their variability depends on basically the magnitude and the luminosity of a star. And this then introduced a new distance measure. So you always, in astronomy, of course, you're missing 3D, so you're always looking for how do you measure distance. And Cepheid stars were a new way that allowed to measure distance, and then to bigger distances than it used to be possible at that time. So right, so I'm also showing these computers. It went on down to, you know, 70s when they were computers were replaced by IBM computers, mechanic computers, but the cheap labor went on calculating things by hand for a while. Okay. Then also in the beginning of 20th century, spectroscopy was invented, and basically Doppler effect. So basically when light would come from a star, it was possible to measure the position of the lines emitted by a star, and it was realized that all of these nebulae were moving away from us. Okay, so it was funny, you know, we have stars and then we have these nebulae and they're moving away from us, you know, what does that mean? And indeed, in the 1920s, there was this big discussion, big debate in Washington, where there were two camps. One camp was saying these nebulae are just weird stars. Another camp was saying, no, these are actually other galaxies. They're like our own galaxies, but we just see them from outside. And that was sort of outrageous thought, like, you know, but yeah. But anyway, so they were discussing and having a whole conference on that topic. Okay. So another technological improvement in that time was by Hubble. Hubble was the PI of the experiment, but basically there was the most powerful telescope at that time, the Hooker telescope in Mount Wilson, California, that was then pointed towards this nebulae. So finally, they had a very, very sensitive instrument with high exposure, and Hubble discovered a Cepheid, actually discovered a star within a nebula, and due to the Cepheid properties, managed to measure the distance and realized this is the much bigger distance than any we know in our galaxy, and therefore these are different galaxies. So basically, this is where extragalactic astronomy begins. We realize there are other galaxies out there. Okay? So very briefly, this is not doing justice to the field, but you all know all these things. In Europe, so while the US had lots of money for new fancy telescopes, in Europe the theory was the king. And so Einstein, of course, developed his theory of general relativity, basically came out with this amazing formula in very compact shape that I will not go into, but basically that connects the geometry of space-time with energy matter density in the space-time, basically. So okay, so he manages somehow to write this powerful formula, but solutions to this formula, it will take a long time to be realized what it actually means. And so slowly after Einstein came up with the formula, there were Friedman and Lemaitre that realized by actually looking for solutions of this formula in particular cases, that they realized that one of the solutions of its formula, or not one, or this solution of this formula is that the universe must be expanding or might be expanding. Basically, of course, this is not a topic here, but Einstein realized that because of the speed of light, you have to connect time and space in the single metric, and that automatically meant that there is no such thing as static time in a space. No? So as soon as you have motion in space, that means things are, not static, and therefore these guys realized that, the universe cannot be static if the Einstein equation describes it. Okay. And so then Hubble actually measuring now, looking at all of these nebulae that were known and more being discovered at that time, realizes that galaxies are moving away from us and the farther galaxies are moving faster, which is basically equivalent to the proof that the universe is expanding. So this is how it would look like if the universe is expanding. If universe is a homogeneous, isotropic, and expanding. I will not go into the proof, but if you even think about the balloon and you put dots and you blow a balloon, you will see that, from one point of view, the farther the point is, the more it is moving away from you. And so basically Hubble proved, that indeed Einstein was right and the Friedman and Lemaitre were right, and we live in the universe in which other galaxies exist, and moreover the universe is expanding. Okay. So this is, basically already by the 30s, due to all this technological, theoretical knowledge, we realized that there is more to the universe than our galaxy. It is expanding, and that this expansion depends on the matter and energy content of the universe. Okay, quite mind-blowing, in such a short span of time. Quite many facts. Okay, but then astronomers, of course, they were very, very enthusiastic about all these discoveries and started measuring with ever better tools farther and farther galaxies and trying to test this Hubble law. Is it really true even in large and larger distances? And in order to do so, they started observing galaxy clusters. Okay, so galaxy clusters are these large objects where you have hundreds of galaxies gravitationally bound, and they're at quite big distances from us. And so they were looking at the catalogs of these clusters and measuring how quickly clusters are moving away from us by measuring how quickly each galaxy that belongs to a cluster moves away from us. But then what they realized is that already in the 30s, when they looked at the coma cluster, they realized, okay, the cluster is moving away from us, but there is a huge dispersion among velocities in this galaxy cluster. So even though all galaxies had proper motion away from us, they had actually very high velocities within the cluster itself. Okay? And so this was curious. But then that led to some people, in particular Franz Zwicky, to basically, for the first time, apply the virial theorem to astrophysical objects. Basically what he said. He said, okay, we know the kinetic energy. We know how fastly galaxies are moving. So he said, basically, let's consider that cluster is like ideal gas. Okay, we know kinetic energy of all galaxies, how quickly they're moving within a cluster, and that will allow us to determine potential energy, meaning gravitational energy within the cluster. Okay. And the gravitational energy, gravitational well of a galaxy cluster is proportional to the total mass of the galaxy cluster, okay? So he was saying, basically, Tricky, okay, we know velocities of all galaxies, okay? But the velocity of galaxies within the cluster is basically just determined by how deep is gravitational well, how much mass is in this galaxy cluster, okay? And so to make a long story short, basically he did a calculation and he realized that actually these galaxies are moving crazy fast, because if in the cluster there would be only, if all the mass of the cluster will be given only by galaxies that we see, they should be moving much, much slower. Like he was saying, this is something weird happening over here. And so he calculated, later I believe this calculation was wrong, but it anyway served the point. I mean, the numbers that he arrived at were not completely correct, but anyway, he realized that basically there must be 400 times more mass in the galaxy cluster than what we see, okay? And he called it, I think, already this dark matter, dunkel Materie, something like that in German. Okay? But people were not worrying yet too much. They were saying, okay, this galaxy cluster is far away. What do we know? Maybe there is some dust, some matter that we do not see. So they were saying this is not missing mass problem, it's just missing luminosity problem. Nothing to worry here. Okay? But however, this persisted. You know, people looked at other clusters. There was always this weird thing happening. So some scientists pursue it. Some were just saying, let's not get, you know, too excited just yet. Then how about galaxy scales? So looking at galaxy scales, people again slowly started to have better instrument and were able, so before all galaxy was just a nebula, no? Now with new instruments in this time, at the second half of the 20th century, they could already measure velocities of stars as you move from the center as a function of distance. And they were saying, okay, let's test this then at galaxy scales. Let's see if stars in a galaxy move faster than they should, okay, as we see in the clusters. Here, in spiral galaxies where you have rotational motion of stars, it is sort of a different kind of virial theorem in a sense that you see the kinetic energy is given again by potential energy, and what would you expect, and this is Kepler law, that if all the mass, like in a solar system, if most of the mass is just in the center, meaning the integrated mass does not change as you go further out, then you expect velocity to fall off as 1 over square root of r. And this is what you observe in solar system, where, you know, mass is dominated sort of by the sun itself. Okay, and they were saying, okay, this is something that we should also see at galaxy scales. If most of the mass of a galaxy in the central regions, then as you move out, we should see such behavior. Let's test it, okay? So they started doing it. Again, always the same concept of not having good enough telescopes at the beginning. So at the beginning, Horace Babcock, this was 39, he started to measure velocities of stars as you move away from the center. But again, telescopes were not good enough. So you could just move a little bit, very close to the center, just a little bit out, okay? So the data was inconclusive. It seemed that velocity is not falling as you expect, but it's staying flat. But again, people are saying, oh, come on, your instruments are not good enough. What do we know? And things like that. All right. But then another technological improvement at this time was also quite interesting, because during the World War, people built lots of radio telescopes to track, you know, enemies and to, yeah, I don't even know what it was used to in the war. But after the war, then there were all these unused telescopes, radio telescopes around. And scientists realized that radio telescopes are actually great because universe is mostly made of hydrogen, atomic hydrogen, and atomic hydrogen emits in 21 centimeters. So suddenly you could explore universe, you know, for free, for the bad reason of having a war before. All right, and so galaxies, as well as they have stars. Okay, so I don't know where is the picture, but galaxies, as they have stars, they also have lots of gas in the outskirts. And in fact, you have more gas than the stars as you move further out. And then in '57, they started measuring velocity, how gas velocities change, and it became clear that actually, it started to become clear that the velocity of gas is not falling down, but it's staying flat as you're moving away. And again, better and better telescopes. There was spectrograph in the 60s and better 21 centimeter observation. They then suddenly, after a while, they proved beyond a doubt that the velocities of stars and gas as you're moving away from the center of the galaxies are not falling down as you would expect, but are basically staying flat. These are so-called flat rotational curves. And so basically, what is that telling us? So I was saying before, like, if all the mass would be in the center, then integrated mass is constant, and velocity should fall like 1/square root of r. But if mass is not all in the center, and in fact, total mass is increasing with r, as we will see is the true for dark matter, then this equation predicts that V should be constant, and this is what you measure. Or saying it other way around, saying it other way around, if you measure flat rotational curves, you go backwards, you see that the total integrated mass as a function of radius should grow with radius, okay? And so basically then it all came together, and more people, or majority of scientists, started to believe that there is some weird fluid in the galaxies and galaxy clusters, this dark matter that was introduced by Zwicky or some other people also at the very beginning as a concept, that it must be there, and that we now, by measuring this rotational curve, are starting to get a feeling of how it is distributed in the galaxy. Okay, so by the 70s, most astronomers were convinced that there is such thing as dark matter. But so then how do we go from there? Okay. So by the 90s, we started to have much more powerful telescope. This is, for example, from Sloan Digital Sky Survey. Here, every dot is a galaxy. So we started to basically measure a significant volume of the universe around us, and to look at distribution of galaxies, and to see sort of what kind of patterns, statistical distribution they have, okay? And so the question then was how this dark matter fits in this picture. Can such measurements tell us more? So at the beginning, with expansion and things, it seemed, it could have been that the universe is extremely complex, but indeed, in the ballpark is not. It was Zeldovich, one of the first scientists, who realized that basically you can describe the main ballpark of the universe in a simple way, because you basically only have gravity and you have, some fluid, say like dark matter. And this is how basically, yes, this is something like this. So he was saying, like, if you have some perturbations, even tiny one, at the beginning of the time, you have some, in the space, in the universe, you have some parts where you have a bit more matter, some parts where you have a bit less matter, okay? You just give it, 10 gigayears, and you will get the galaxies as you get now. Because where you had a bit more matter at the beginning, the gravity will pull in more matter, and you will grow perturbations, and where you had less, you will grow voids, and at the end, if you just put it in, say, nowadays, or even like here from the 70s, we had this, started to have these n-body simulations where basically we put tiny perturbations in the field, in the gravitational field at the beginning, and then just let gravity work, and we start to see that after lots of time we start to develop these structures where, again, each point here is the overdensity, where you have more matter, and this is where galaxies would develop, or clusters of galaxies would develop. And so basically what I'm getting at is that people realize that you need such thing actually as dark matter even to get to this distribution of galaxies that we see today. And why is that? It is because, you need these gravitational, these perturbations to go one fast. In a sense, you need more dark matter than you see baryons. And they have to also be sort of not interacting. They have to be slowly moving and not interacting with photons or other particles, so that they can just be attracted by gravity and stay and sort of provide seeds for this growth of perturbations. So basically, again, this is the same thing. People started developing n-body simulations, comparing them to observations. And they also realized this thing, right? If you would have dark matter, these perturbations would grow very quickly, and you would have no dark matter, perturbations could be erased rather easily, because you have baryons that have pressure, there is not enough of them, and the perturbations not be growing just as quickly as without dark matter. And basically they did, these are some early simulations, I guess, but basically there was a clear prediction that if you have dark matter that is slowly moving, this is another point that I will stress later, that is non-relativistic, basically you form structures like this, and if you have no dark matter or some very fastly moving dark matter that is basically massless, like neutrinos or photons, like something that is not heavy enough, it's moving with the speed of light, you would have image like this. And then, of course, because what we measure assembles it has much more structure. It has structure on every scale. This is another sort of proof that we do need dark matter even to have the structures that we observe in the universe today. So now the evidence is becoming more serious. No, like first it was galaxies, cluster, but who knows? But now basically the universe needs to evolve over 10 gigayears. I mean, in order to evolve, as we see it evolve, you do need it over all times in the universe. Another line of evidence is the so-called given by the cosmic microwave background. So here I would, I don't know how much cosmology you had, just very basic. I mean, CMB can be studied for months, but here is just a very quick recap, because as we are going on from early in the universe, there were different ages. I'm sure you studied it only in cosmology, but what happens at some point, 400 years after the Big Bang, at redshift around 1000, is that before this point, you have hydrogen ions, universe made mostly of hydrogen ions and photons and electrons that are all interacting with each other, okay? And basically they make this like plasma that is interacting, that has pressure. You also have dark matter, but among charged particles you have electrons, photons, and charged nuclei that form this plasma that interacts. But then at some point, basically electrons, molecules form, electrons attached to atoms, universe becomes neutral, and suddenly there is no pressure anymore. Like you just form molecules because, I'm not going, but because universe cools down enough, you just form molecules, and then photons are basically free to stream. They don't have anything else to interact with. So this is sort of there be light thing, like it just light starts, starts to go, starts to stream without any interactions to the universe from that point on, okay? And that's why the photons then emitted at that time basically give us a snapshot of the universe as it was then, okay? Because those photons get redshifted, of course, because the universe is expanding, whatnot, but they interact very, very little. So they just basically, you see, it's really just like taking a picture of the universe at that time. Okay, and so what can that light tell us, okay? So basically what was happening, I was saying something about this pressure. Before photons decoupled, I was saying you have this pressure made of, this fluid made of charged particles and photons, okay? And so photon pressure resists compression, okay? Because basically you have this, you have gravitational wells. You have charged particles that want to fall on gravitational wells and just form, structure very close by. But then you have photons that interact with that and trying to push the particles away. And this is something like acoustic oscillation, basically, effect, because you have pressure. This pressure, again, has this sort of, you can imagine it as a harmonic sort of as a spring, because you have this sort of motion of particles infalling in gravitational wells and photons pushing them sort of out, exerting pressure. But this pressure that you can see as acoustic pressure, they call it acoustic because basically what matters is in this baryon photon coupled fluid, what matters is the speed of sound. I mean, I know it might sound confusing. Why do we talk about sound now that we have particles, electrons? But it is because when you have coupled fluid with pressure, you talk about speed of sound as the velocity of which information perturbation travels. So in this sense, this is acoustic. These are acoustic oscillations. Okay, but then these oscillations are imprinted in temperature because when you have higher pressure, you also have higher temperature. And so basically you have this sort of oscillating pressure that basically imprints in temperature, and temperature photons that then you see later. It's not trivial, but it makes sense. so yeah, okay. Okay, so basically what happens here is that you, what do you want to say? Right, so what happens physically is that you have these regions where you have high gravitational potentials, you have this region with changing pressure, and this pressure is connected to changing temperature, and then at some point it's all released because there is no more the pressure because just photons come to us and you just take a snapshot. But why is that important? Is because, so what is the physics quantity that you are taking away from that? So what you're taking away from that is basically the scale. There is a particular scale of the universe that is basically the length which speed of sound can travel in a horizon time. Okay, so thank God. I mean, this is when it gets a bit tricky to explain in 3 minutes, but basically, in this universe, in this picture that I was telling you, basically there is a particular length at the time of CMB, which is how much basically one oscillation can happen in these gravitational perturbations. Okay, and this length turns out to be 1 degree. Okay, this is what is measured by CMB. So CMB, you measure perturbations. When you make Fourier transform of perturbations, you see that you have perturbations happening on different scales, and the most significant scale is 1 degree. So this 1 degree gives you the distance scale, how much the sound could travel at the time of decoupling, or the CMB decoupling, and that is related to the speed of sound, and speed of sound is related to how much baryons you had there and how much photons you have there. Not important that you understand details, as I said, CMB is the course on its own, so it's not, but just buy it now, because the only things that I want to say here is that at that time of CMB, you had interaction between baryons and photons that determine the speed of sound, okay? And this speed of sound you measure through CMB, like that determines you the scale, the most dominant scale in the CMB. Okay, so basically you have a way to measure how much baryons and how much photons you had at that time. You also have a way, I mean, in the theory, it also, what plays in is how deep these gravitational wells were at that time. And that is given by dark matter. Because as I said, dark matter, we realize there is much more dark matter than normal matter, and the depth of wells is dominated by how much dark matter you have. And so to make long story short, basically CMB gives you, you can measure many things due to CMB, due to the position of the first peak, due to the height of the first peak, positions of other peaks that are, okay, just Fourier transformation. But basically, cosmic microwave background gives you a way to disentangle the dark matter component, which tells you how deep are gravitational wells, and baryons and photons, which provide pressure. And so you can play, there is this tool, for example, here, CMB plotter. So as you change amount of dark matter, you get very different, CMB. As you change the amount of baryons, you get very different CMB. So basically, in order to fit all these peaks and their heights and their positions and everything, you basically can constrain rather well how much baryons we had, how much photons, and how much dark matter. Again, long story short, you need dark matter, and you need it in the amount that we know today in order to explain also CMB. Okay. So let me see what is okay. So basically, by this point, and by that point already, there was this like strong, conviction in the community that dark matter should be there. Okay. Still, it is a very weird thing. So we are always trying to find loops in this reasoning. But the evidence was getting just stronger and stronger in time. I just have a little detour here, focusing on galaxy clusters. Okay, so galaxy clusters are the biggest gravitationally bound structures that we have in the universe. There are such things as superclusters as well, but let's leave that. Those are let's leave that on the side. So these galaxy clusters are full of galaxies and full of dark matter. And I said already, due to the velocity dispersion of galaxies, we already discovered dark matter in galaxy clusters. But galaxy clusters can provide also different probes. For example, galaxy clusters are full of gas. And the same game can be played like with galaxies. The deeper gravitational well, the hotter the gas, and so the higher the X-ray emission, the temperature as measured by X-ray emission. So again, by measuring the temperature of the hot gas, you also realize that there is more matter in galaxy clusters than what you see. Yeah, I think this is also shown here. You measure just the Planck, the temperature of the gas, and you see that if you want it to be so hot, you need to have much more matter in galaxy clusters than you see in stars and gas. Another way how you can use galaxy clusters is through gravitational lensing. So if you have some faraway galaxy, you can look at gravitationally lensed images of a galaxy, and lensing will depend only on the mass of the galaxy cluster. And again, by analyzing these images, say of a blue galaxy in a background, how its image is distorted by the gravitational lens, meaning the mass of the cluster, you can determine very well the mass of the cluster, and again, see it's always consistent with all other measurements, see there is dark matter. But there is one more thing that galaxy clusters gave us, and this is now this story of the bullet cluster that you probably heard about, because as everything in the universe, things are not static, as we said, and you have many mergers. You know, galaxies merge, galaxy clusters merge, okay? And so then people started looking, okay, let's look at merging galaxy clusters, okay? These are these enormous objects interacting with each other. What can we learn about dark matter there? What happens there? And so then in this paper, very important paper of Klav in 2006, they did this observation in 3 wavelengths, in 3 ways actually. One is optical. So here, I don't know, you do not probably see very well, but there is overdensities of galaxies, I guess, here and there. Let's see later. I'm not sure anymore about the position, but from the distribution of galaxies, you can see, you know, where galaxy clusters are just in optical. Then, if you look at X-ray gas in this direction of merging galaxy cluster, you see that X-ray gas has this shape and this weird bow shock shape here. Okay, so this was very interesting and indicating. And then they were also lucky that they could get very nice gravitational lensing images of mass in these galaxy clusters. So basically, behind these 2 clusters, there were good galaxies that provided very nice images of lens, and they could see through lensing where most of the mass of these galaxy clusters are. Okay, and so when you combine these images, they came up with this amazing picture in which you basically see that after interacting these 2 galaxy clusters, the dark matter basically and galaxies that interact not strongly, just with gravity, they pass through each other. 2 galaxy clusters pass through each other, while gas that has pressure, that interacts, you know, electromagnetically with each other, was left behind and developed these shocks, bow shocks in the galaxy. Okay, so this was amazing discovery, because before we were always saying that where you have dark matter, you also have baryons, and we understood that where you have dark matter, baryons follow gravity and they just stay. But now you see, if you have merging system, if you have dynamical system, what happens? You can have dark matter displaced from baryons, from mass. Okay. So this is a new knowledge that we gained, that it's not that they always are together, okay? So since then, I'm not so updated, so there was a couple of more of these examples of merging clusters. There is this Abel 520. I guess this is gas, and this is mass. And then there was this mask thing here, where you also see this displacement. I think there are many more examples, but I could not Google them very quickly. Okay, and so basically, in summary, we do have evidence for dark matter in a wide range of scales and throughout the history of the universe. So from large-scale structures, galaxy cluster galaxies to the small dwarf galaxies. We will talk about this. So these guys are tens of megaparsecs large, and dwarf galaxies are like kiloparsec or so. And all these scales, we have this evidence that there is this additional mass needed. So here is this pretty picture from University of Hawaii. They have a telescope that basically measured the gravitational distribution of mass in our neighborhood. So I guess we are here. Here are the close-by clusters, and they believe that they measure this local supercluster, so how mass is distributed around us in this filamentary structure that we see anywhere else. So this would be supercluster of hundreds of megaparsec size and 10 to the 17 solar masses. So really like huge, huge object that apparently is all still to some degree gravitationally bound. So they have, this is even nicer picture. So this is like sort of our cosmological neighborhood. They call it Laniakea, immeasurable heaven. Okay. Okay, let me just see. Okay. All right. So how much time I have, just that I know where I'm at? Okay, so I'll see. I just have a few more things here. So again, this I already said, what we know, but just I wanted to point out that all evidence we have so far for dark matter is gravitational, okay? So it's only through gravity so far that we know that it is there, and it's in astrophysical system, so not on Earth. It's always we see it far away, and we see it through gravity, okay? So this is not really super settling. We would like to know more. And so the question that people asked, rightfully so, and are still being asked, but it's much more challenged now, there were these options. So one is this there is such thing as dark matter. There is such thing as dark matter fluid. We just do not know what it is. We will discuss what it can be. Right, we just have to add something to our world, some new substance, okay? Okay, but other possibility was this, that because we only see it through gravity, maybe something is wrong with our understanding of gravity. Maybe the Newton law, the laws of gravity that we know, maybe they're not true. Maybe they're true locally as many other things, but if you go to cosmologically, maybe just we should change the laws. Maybe you do not need a new source of gravity. Maybe you just have to change the law of gravity. Okay, and this is very fair question. In fact, it's very reasonable thing, but it's challenging that it can work. Okay, so the idea, I think, so I'm not very knowledgeable. I think some people here maybe know much more, but the original idea Mond, and then it has more and more complicated and more developed incarnations as we go in time. But the basic idea is very simple. It's basically saying. Like this. So this is a Newton law, F equals m times mass times acceleration. But then it was saying like, but maybe this is true only for small accelerations. So that like, no, for large accelerations. So if acceleration is larger than some constant on Earth where you have lots of mass, if acceleration is larger than some constant, then this mu could be 1. But if you go to larger distances where there is lots of empty space and you have small accelerations, then this does not need to be constant, and it could be some function, and basically can be proportional to acceleration itself. Okay, and then if you play this game, you can produce these flat rotational curves you basically can produce these flat rotational curves for a given constant A0, okay? For a given scale of acceleration for which this transition happens. And so this is amazing. So just by modifying slightly, Newton law, apparently, dark matter in galaxies goes away. So this is great. But there is a problem because, as I was saying before, we observe dark matter on very big range of scales. So one constant that you obtain by fitting galactic rotational curve does not work for clusters, does not work for dwarfs. It has lots of challenges. Then you can complicate a bit the function, but then it starts to become less pretty, and at some point dark matter becomes simpler, simpler solution. Let me just see. Right. So basically, this is argued in this in book of Scott Doddleson. Basically, what this shows is how dark matter clusters. And what you should know, I will not go in details of this picture, but this is showing how much power of clustering you have on different scales, okay? And so what we know for dark matter, that basically you have lots of power. I mean, if you normalize it properly, it's basically constant power on all scales. It's like fractal-like, not really mathematical fractal, but in a sense of a fractal-like structure where you have power on large scales, but then smaller and smaller you go, you always have the clustering, you always have perturbations on every smaller and smaller scales, okay? And this is something that you cannot get by modifications of gravity of that kind, because every scale would sort of, yeah, it's very hard to get it in different way, because you would have to introduce constants basically following different scales, or do something more fancy. Again, I'm not very knowledgeable, but this is really a challenge for MOND-like systems. And then in addition, there is this bullet cluster that sort of, okay, people can argue now, is this really proper measurement? Do we have enough data and things like that? But this really shows, because in MOND-like structures, it's telling you there is no dark matter, it's only baryons, and gravity is modified. But then if that is so, then this shouldn't happen. Then where you have baryons, you should also have the gravitational interaction. You should always also have this additional mass. So the bullet cluster is one of the biggest challenges for these MOND-like systems. And so then, so then we will work in this framework that it does exist, and work how to find out more. I do not know. We could stop here, or I could start with next lecture, but maybe we can take it a bit easy. I don't know if it's too easy. I wanted to start with a nice story. How many minutes? 5 more minutes? Maybe I can then, okay, maybe I can then start, just then later we have more time. Just, I have to go to the second lecture. Where's Tiago? Maybe I will find it here. Yes, maybe you ask if you,
So in the beginning, you were showing something about the MOND.
The MOND.
Yes. And case.
I just start the second one. Yes.
We have a scale.
No, the second one. Yeah, you can start the second.
We have a constant acceleration.
Right.
And in this case, when we apply it to the curves of galaxy rotations, we have many different kinds of galaxy rotations.
Yes.
Shapes. Then we can always change this
right.
value.
It's not really so much because galaxies typically have this scale of, I don't know, 30 kiloparsecs or 200 kiloparsecs. Yeah, I mean.
But but the point that I want to go is that when we think about the structure formation, I think MOND does not apply anymore because it's larger scales.
Yes, it's very hard to, exactly, that's the point.
So in this case, they have a kind of, how can I say, forget the word, but it's like they come back to general relativity because now they have no support.
No, exactly. No, you're right, exactly. That's true, because if you go to very large scales, right, it's becoming very hard to implement it. Then there is this TAVs, like this relativistic version, but it becomes quite complex, and at that point, probably it's not motivated
Also, I think I saw something in these last months, because they were arguing that it's possible also to explain the bullet cluster using MOND.
Right. No, I know that there is research going on. So it's not that. But I'm just saying it's really challenging. It becomes a question on the taste, like how much at some point introducing dark matter becomes a simple version of that. Yeah.
But again, I think I follow the same point because they are always changing. There is no kind of a structure that remains when they are trying to explain
universal.
Yes, the complementarity of this phenomenon they cannot explain with one word.
Yes, exactly. So right, if you want to go a bit more, let me just see this. I'm just want like so very. Sorry, I'm touching things. Like, it became very hard to deal with somebody else's computer because this touchpad. I just want, here maybe it's here. No, this is sharing, sorry. This is just sharing on Zoom that he's doing. Okay, sorry. Maybe do you know? I mean, I think he had a folder with both talks. Was that the, ecco. So it should be this one, yes. Good, so I think it's good to go, yeah, perfect. I'm not sure if you're sharing with Zoom also this screen. We are sharing, okay. Maybe just the whole screen start. Is this the one? I'm not sure. No, or maybe. Okay, good. Thank you. All right, so just 5-10 minutes more. Okay, so then what do we know about dark matter, okay? Assuming it's a particle. Okay, so one thing, as we were saying before, we know that it was present at least since CMB, we'll see, since Big Bang, basically. But since very early, we need it to be present in the universe. And therefore, if it is sort of some particle or something, if it's some particle or some object, it has to be stable. It shouldn't just decay to normal particles at some point. No, it has to be present all the time. And so if you're building particle physics, building your model, basically the lifetime of a particle, or again, maybe some astrophysical objects, needs to be at least as long as the age of the universe. So you will see, we'll talk about this later. This is already a big challenge because there are very few stable, really stable particles that we have. So it's an trivial constraint. We also know its amount. So this is something that basically comes from the CMB that we were talking before, because as I was telling you, as you change amount of dark matter, the CMB features change a lot. So this is not the only measurement that determines the amount, but it's one of the more precise, that basically tells you that in the universe today, we have, say, around 5% of ordinary matter, then about 5 times as much dark matter, okay? So this is, as far as matter is concerned, dark matter is the king. No, you have much more of that than the normal baryons. Then, of course, there is huge elephant in the room that nowadays, most of the energy matter density of the universe is given by dark energy, which we have much even less, hand-waving argument what it can be, and we will not talk about today, okay? But yeah, we'll just focus on the matter part of this spectrum. Okay, so we know it's stable, we know its amount. We also know that it is electrically neutral, because for everything that I was telling you, we were saying it does not interact with photons. So photons interact with electric charge, and so dark matter should not have electric charge. And so if you then look forces with which it can interact, so you have gravity, electromagnetic, weak and strong forces. So we know it interacts through gravity. We know it does not interact electromagnetically. Strong interactions are strong and have confinement, so this is not something that dark matter seems to be doing. And then you have these weak forces that we know of, and that could be okay. In a sense, weak forces have long range, they're weak. And so when we now think about how dark matter interacts maybe with itself or with other particles, we think something like weak like force. You will hear me saying this as we go along. But now let's check this electrically neutral statement, because it is always a question how much. I said it does not interact electromagnetically, but people throughout the history try different things. Basically, they were saying, okay, it's not really interacting as strong, it's not really doesn't have electrical charge as much as normal baryons, but can we check if there is some weird charge happening on Earth that we do not know about? For example, if dark matter would be positively charged, it could form bound states with electron and form heavy hydrogen or some elements like that. Or if it would be negative, it could form to the nuclei and form some anomalous isotopes. Because you always have to ask yourself, many times you think, this must be excluded, but when you look in the data, is it really? And so people play this game. So I even forgot what it was. This was a long time ago when people were still trying to catch maybe charged dark matter on Earth, but all of them gave negative results, and it's really, with high precision excluded this possibility. So then this is what I was saying. So if it has non-gravitational interactions, they must be weak. At the beginning, people really talk about genuine weak interaction, really exchange of W or Z. This is excluded now, but something like that is what we will be imagining. Then it should not be baryonic. So what does that mean? It should not be some like baryons even without a charge. Basically, this is again similar to what I said before. It should not form atoms, okay? And why am I saying this? Because one of the, again, very precise, not very precise, but one of the early measurements that we have in the early history of the universe is this event that is called Big Bang nucleosynthesis, when basically atoms formed, like hydrogen, helium, deuterium, and so on, when the particles came together and formed nuclei, basically. So it's a nucleosynthesis. When protons and neutrons came together and formed various nuclei. So what we know, and we have a very good model of how that happened, model that depends very closely on how much, protons and neutrons you had at the beginning and what could bind to them. Okay, so the point here is that, and this is really constrained quite well. And so basically what we know is that any model, any candidate for dark matter that you have, it shouldn't be such that would bind to these elements and mess up with Big Bang nucleosynthesis, okay? Because this is, again, one of the earliest tests. So we have these very precise models that are based on normal particles that participating in BBN that is verified with high precision. So whatever candidate you have should not have anything to do with baryons at BBN. It could interact with baryons maybe before nucleosynthesis, but not after that. I mean, much before, but should not participate in Big Bang nucleosynthesis. 5 minutes, okay, perfect. I think I'll just go through the properties and I'll stop there. So then, all right, so another thing is, again, something that I was mentioning is that it needs to be non-relativistic at time of formation of first structures. So what that means? So if it is a particle, it should be such particle that it is heavy, meaning non-relativistic, meaning it needs to have velocity much smaller than the speed of light, at the moment when structure started to form, okay? So why I'm saying when structure started to form, I was telling you before that since the beginning of the universe, you basically have these little perturbations. But perturbations were not growing fastly from the beginning, because at the beginning you had lots of photons. Very, very early in the universe, you had lots of hot stuff that was slowing down the growth of perturbations. At some point, after photons decouple and so on and so forth, perturbations start to grow much faster. And at that point, dark matter needs to be there non-relativistic, in meaning that it should allow the fast growth of perturbations. Because again, if there is no dark matter, or if it's warm, meaning relativistic or mildly relativistic, it would erase these perturbations. And again, we know that the universe we observe now is like this. It has lots of small structures. Otherwise, we would observe the universe like this, where all the small structures are erased due to the motion of relativistic particles. So we basically know the dark matter should have a KV. If it's thermally produced, it should have a mass of KV or so, or above. Again, I don't want you to be confused if you're not really in dark matter business, because axions, for example, the particles that Manuel will be talking about, that axion-like particles are good dark matter candidates. They're much lighter than KV, but they're not thermally produced. So you could have particles that are very light, but still not relativistic, okay? Just be careful. So we need it only to be non-relativistic. If it is thermal, then it means it has to be heavier than KV. Okay, so this is the checklist, what we need dark matter properties to be, that I just said. So maybe I just go slightly more. I'm so happy if you're going a bit more, because that means I'll have more time. I can tell more in the last lecture. So then so now we have this challenge. So what it is? Is it a particle, or we'll see, or astrophysical object? How does it couple to standard model? And does it couple to our standard model with some other force rather than gravitational? And then things that we would really love to know but are not even getting there is it a composite or elementary? Like, is it really elementary particle or it's some sort of atoms? Is it maverick? Just you have one dark matter particle or you have full dark sector? So all these are questions that we really hope we will sort of discover the whole dark world, you know, as we go, but we're still very far from that. So I think that now I will really, stop, because then we will talk about dark matter candidates then in the second class. Okay, thank you. Yeah.
My question is, do you consider if we had a gravitational theory at quantum level, it would be possible to find an evidence of dark matter at that scale?
On which scale? Sorry, I did not hear.
Quantum scale.
Quantum scale. At the tiny scales, you're saying. Well, we do not know. I mean, as I was saying, like all the evidence we have is from astrophysical objects that are rather large. So we do not have evidence at tiny scales, because at tiny scales, because we have evidence through gravity, and on tiny scales, gravity is subdominant force. Usually tiny scales, you have other forces like strong force, electromagnetic force, and things like that that mask the effect dark matter would have. But it's very possible. There are such theories that couple dark matter and dark energy. You know, in particle physics world, you expect it to, you know, to be a particle or to be, I mean, we'll talk about candidates to have, if it's a particle, it definitely has effects also at the quantum level. But I don't think that now we have strong evidence about that.
Okay.
Hi, thanks for the lecture. My question is not very scientific, but what is your guess?
Right, so oops, sorry. What is my guess? You mean among dark matter candidates, I guess? Well, maybe let me answer. I mean, I don't have actually the answer. I will tell you that it's really tough making guesses in science, because there are such a beautiful theories that you say, my God, like I really vote for this, like this must be true, and then it's not. And so, it's very painful to, you know,
Fair
have
enough.
favorites.
Thanks.
Okay.
Also, head out for lunch. Let's thank this week again.
Thank you.